as well. Now, I was setting this up earlier. I can't recognize the slide because the print's so small. Where in the world? I guess this is from the previous edition.
It's, yeah, the first theorem in 14.4.
Okay, 14.4. That looks a lot like it. It's almost that, but not quite. But we can go from that. Yeah. But it looks like it's avoiding the L of X altogether, which I give a big hip hip hooray for, because that was, to me, I found more complicating than it was worth. So I think we can live without this one. So to me, I think someone in the last class must have thought this a little bit on the way out. That's the best I can do for now, I think. And here's Nigel. I'm going to stand in front of this so I can feel a little heat coming off the bulb. All right. The other announcements I was going to make are these. Wednesday's that day you've been dreading all term, last day of class for this course. Okay? Yeah, and the papers are due in then, and I want to return all of your tests then. At least all the ones you've turned in at that point. So that means I'll need them all to be in by Wednesday. If you can get them to me before Wednesday, I'll try to have them graded and back to you by Wednesday. But if you don't get them to me by Wednesday, I mean before Wednesday, I need them on Wednesday so I can return the others to them. I don't want the correct answers floating around out there while you have, still people to turn in the test. So please try to get everything in by Wednesday. That's the paper and the tests that are been out so far. We'll cover as far as we can in 14.4 today, and hopefully maybe even get into 14.5. Okay, I doubt if we'll get through 14.5. It's a long, long section, but let's at least try to get there. Now, what that leaves off is the chain rule, which is great, but it's nothing new. I mean, I think you'll see it's exactly what you expect it to be, and but that means I'll only test you as far as we get today, okay? And that means I've either got to make up a new test or have a few questions on there that'll be bonus for you. So I'll do one of those. Yeah, and that's probably what it's going to be, because it's going to be easier to do. So anyway, we will go from there. All right. Oh, student course evaluations. Please get those done as soon as you can. I mean, you can wait till the end if you want to, but just don't forget, okay? I tell you, when I walk in this classroom and look out there, I'm expecting to see snow. I know it's not that cold yet, but it just feels, and all the leaves are off the trees now with all the wind and rain we've had. It just looks more wintry now than it has yet. All right, any questions for anything we've covered up till now? Okay. Now, we were talking last time about local linearity, okay? And I guess that's what this slide was. I'm not going to focus on it because actually I'm preferring that we not go into this, but I'll just sort of give you a feel for what this is saying, because it is leading to something we're going to do next. Sort of the linear approximation of a function would be pick the value at some point, and then do in the x direction, the f sub x at AB is going to give the slope of the tangent line in that direction. and multiply that by a minus b, slope of this, and basically you've got a good approximation for the value of the function in any xy near ab. The key there is near. How near is that? And if it's a locally linear function, that's going to be pretty close, as long as you're close enough. The xy is close enough to ab. Now, this is the better representation of what I was just trying to say with my arm waving. This, well, all right, there, it took that time. All right. Here's your z is equal to f of xy, the blue parachute under there. Here's your xy plane, which defines pretty much the domain of that function, wherever that's going there. Come out here to some point A on the x-axis, B on the y-axis, and go up and find your function value, f of AB. Well, that defines a point that's on this graph, the blue curve here. P of A for x, B for y, and f of AB for z. That's on there. Now, your partial of f with respect to x, that's holding the y constant. The y constant would be at b. Y is equal to b. And this is your tangent line that's along that curve, part of the curve where y is b. This is your x function going f. The x variation of the function is going like there. There's a tangent line to that. If you hold x constant at x equal a, the partial of f with respect to y would then be the slope of that tangent line of the curve where x is equal to a, where that intersects the function value. Those two lines then define the plane, and that's called the tangent plane, okay, at that point. This is really the only point that may be on the function itself, on the blue parachute. But these others are pretty close, at least within a fairly close proximity to AB. Okay? It depends on how locally linear that function is. Okay? Now, this one shows you how far off you are. Of course, at point P, you're right on the money because you had, and now they've rearranged everything here. I'm not sure why they did that. But here's the point A, well, maybe not. Maybe that is still the point AB. They just haven't shown the X, Y, Z axes. Okay, so here's X, AB, and there's your point F of AB. Now, what the previous slide was showing, which they're not focusing on, in fact, in the new book, in the new text, yeah, they do show that L, yeah, it does show up here later. So you're right, Matt, it was shortly after where you pointed out. And it's almost the same. How far off are we to use that plane? But on this picture, figure 3, they don't list the L of XY, but that is that linearization, which in this case is the planarization, is the tangent plane at that point. This gives you a good approximation. And you see anywhere around in there is pretty decent. Let's come out to here, say, some XY at some distance D from the point AB. Well, the error here is going to be the difference between f of xy, this point, on the blue parachute here, and L of xy, which is on that linear approximation, which is actually a planar approximation of it. And the difference between those two is your error. And as long as you can keep the D small enough, your error is going to be small enough. And D is basically, think of it as a diameter. It's a distance, but it's how far from this point you are. And as long as that's a reasonable amount, you can live with it. Okay? Now, that then leads to, why do they have, let me skip this for now. Remind me to come back to it. Here's Theorem 1. Again, the slides are out of order. They sort of took a new approach in the new book, new edition.
Theorem 2.
Oh, this is Theorem 2. Okay. Well, then Matt was pretty close to on the money. This is awfully close to what they have in Theorem 1 in the old book. They just didn't make it a theorem here. Okay? What they said here, Theorem 1 in this new edition. And by the way, there was some stuff that went ahead of this. And it's a good old, say again? Yeah, discriminant cross product, okay, that we do here. Goodness, I'm so cold. Now let's consider, before we get to this, now consider the tangent line in the plane y is equal to b. That's what we've been talking about. Let's go back, see. That would be forward in this. Y is equal to b, that's, here is the line y is equal to b. Here is the tangent line, that tangent to that function that y is equal to b. Okay? That's where they're starting at the top. Now consider the tangent line in the plane y is equal to b. The slope f sub y at AB. Yeah, okay. Hey, it should be f sub x, shouldn't it? Because I think they've got the subscript wrong. Because that tangent line, y is equal to b. Y is equal to b would be everything in this plane here that cuts down through here. Y is equal to b. That's the tangent line. That's f sub x, not f sub y. Because f sub x is where b is y is constant. That's constant b. So I think they got the subscript backward. Okay? Victor came sneaking in trying to get by me, but I caught you. Okay. You look as cold as I feel. Okay, so I think that's with slope f sub x AB. To stay on that line, we can move 1 unit in the positive y direction from AB to f of AB to f sub y AB, units in the positive z direction. From that point. Boy, has that ever a awkward sentence to try to follow. That is to say, the vector defined by v is equal to 0, 1, f sub y of AB. 0, x, 1. That's still a rather bizarre expression of it. Lies on the tangent plane and therefore lies in that tangent plane and therefore lies in the tangent plane. Am I reading that wrong? Oh, tangent line and therefore in the tangent plane. Okay, I was reading it wrong. Thus we have two vectors that lie both in the tangent plane. They can never be parallel since one line lies in the plane x equal a, the other in the plane y is equal to b. The parallel vectors in these two planes would have to be vertical. Okay. So basically what they're saying is you got these two vectors, one v and one u. Okay? And what they do with them is the first being 0, 1, f sub y ab, and the second one being 1, 0, f sub x ab, and you do the cross product, and let me go on and do that. If you remember, the normal vector, I'm not sure if this is a normal vector, just some vector n that is the product of these two cross these two, v cross u, or do they see? Yeah, that's how they do it. Okay, and how you do that using the determinant for the cross product, I say I and write j, I, j, k, and the first one they're doing is 0, 1. Why this order, I'm not sure. F sub y of AB. I would have done it the other one. 0, F sub x at AB. Okay, that's your z value at those points. Okay, and if you did that cross product, it gives you a vector. For the I component, it's f sub x at AB, and this will be plus 0 because that's going to give you a 0, and that'll be your I component. And then when you do the j component, wiping out those two, let me erase so it gets a little less confusing here, maybe. The j component, 0 this way, but you got a, yeah. Now, if you remember the sign thing, if you don't like to remember that, go on and put your I in here again, 0, 1, and when you do your cross product there, that's your f sub y at AB j. Okay, and then when you do your k one, you didn't have to do the next two out there, but that's just going to be plus k, or I'm sorry, minus 1. So I think it will be beneficial, but j 1, 0. Okay, and then when you do that, you get 0 there, minus 1 there, minus k. And you would have gotten the same thing here. You didn't have to have that third one. So. But anyway, there is your vector, and I put it ijk, they put it as in angle notation, f sub x at AB, comma, f sub y at AB, comma, -1. Okay, that is this n vector. And the reason I don't call it a normal vector, though it may be, it's not your unit normal vector, which we usually use that symbol. I'm sorry. No, that's right. That isn't necessarily a unit, so it could be normal. Now, and that is, they say it is a normal vector for the tangent plane and the point P on the plane, so we can write down the equation of the line. And if you remember, if you have a normal plane and a point, a normal vector and a point, these are the components of your line, and f sub x, a, b, and that's time your x minus a, because you're, goodness gracious, throat hurts so badly, plus, and this is the coefficient of the f sub y at AB, and that's times your y minus b. And then we would have, and we do, a minus 1, and that's so minus 1, think of that as your coefficient here, times z minus f of AB. Because if you think about it, your z component is f of AB. So that's why it looks a little different there, because this is just x minus a, y minus b, z minus c, you might say, but you see is f of AB. That's the point on there. So that's why it looks a little different there. And that's equal to 0. That's the equation of the line. Okay. Now, except that's no longer just a line, that is actually a plane. And that then gives you this, okay? This is what it appears to be, and it's really pretty close to this, okay? Say again?
Pretty sure the only difference is L of x, y is a z.
Exactly. That's it. If I could get my voice to work, okay? It looks almost exactly like this with the thing. Instead of z, we're calling it L of xy, okay? If f of xy is locally linear at the point AB, then the tangent plane is given by this equation. Now, they don't call it a tangent plane here, they call it a linearization, which is not really a great word because it's a planarization. So let's just call it the equation for the tangent plane. Z is equal to f of AB plus f sub x at AB, x minus a plus f sub y at AB, times y minus b. By the way, how we got there from here, what you did is add z over here, and then you got z is equal to f of x at AB, x minus a plus f of y at x minus b, minus plus f of AB. Well, they put that in front. So that got you exactly there. Z over here, and then put this in the front of there, and you got this, except with the Z instead of L of xy. Okay, this is like playing musical slides here as I'm sliding around the floor. Okay, and then we got the, and that next line, and this may be what you're talking about. Right under that, we define L of xy to be that. Okay, I didn't see that. I see what you're saying now. That came up there. So rather than it being a focused box here, they've just presented things a little bit different order. Have any of you got the old book? Okay, this follows exactly the old book. No, it doesn't. Wait, yeah, you got the new one. Hold it up. No, you got the old one. Well, there's no theorem 1 with this in it. Okay. That's the first thing. That's why I say yours is following the slide set. Okay, because this is from that book. Okay. So it just is a little bit different approach from it. About it, whatever. Okay. And I think we've just hit the other two slides here. Those two are the slides just below Theorem 1. Now we're ready for the definition of differentiability. Not that it matters that much, we just do it. But I guess it is, for completeness sake, we ought to have the definition. So what's our assumption? Assume that f of xy is defined in a disk D containing the point AB. F of xy is defined somewhere in that disk is AB. Okay? And the f sub x of AB, that's with y being constant, y equal b, and f sub y AB, where x is constant, x equal a, they both exist. So your slope, your tangent, partial derivatives exist at AB. Now, this f of xy then is differentiable at AB if it is locally linear. What do we mean by that? The f of xy is that linearization, which we were calling the z, they're calling the L, plus the area function. That the plane defines a certain value, then you add or subtract the error from it, and you get the function exactly. What is that error function? It's the limit as xy approaches AB, as this is getting closer and closer there, of this thing here, divided by the distance. That's the distance between xy and AB, right? X minus a squared plus y minus b squared. That's the distance between those two things. As that limit gets closer, as xy approaches AB, this is getting smaller, but this area is also getting smaller, so you have one of these deals if that's 0. In this case, the tangent plane to the graph at AB, f of AB, is the plane with the equation L is equal to L, Z is equal to L of xy. There we have it. That ties the two together. Explicitly, Z is equal to f of AB plus f of x of AB times x minus a plus f of y of AB times y minus b. That is it ties those two together. And that's how you do it. So basically, if you have a function, both of the partial derivatives exist, okay, on some disk, okay, around the point AB. Then to find the equation of that plane, all you need is f of AB, which you should be able to calculate pretty easily, f sub x of AB, which you know by your condition here has to exist, f sub y of AB has to exist. Take this one multiplied by x minus a, this multiplied by y minus b, and add to that the f of AB. Z is equal to that. You've got your equation of the line. Seems like we should be ready for an example then, but they do throw in one more theorem. Now, in the new edition, this is theorem 2. This is the criterion for differentiability. Okay, can't get it to take. All right. Yeah, it did it again. All right. If f sub x of xy, and f sub y at xy exist and are continuous on an open disk D, well, that sounds like the conditions of the previous one. Then, and well, the previous definition, this is out of the theorem. Then f of xy is differentiable anywhere on that disk as long as those two are continuous. Okay? Now, I think we're ready for example 1. Is this the figure for it? I believe so. Okay. Show that. I'll blow it up to begin with, but as soon as I go to write on it, it's going to have to shrink back again. All right. Show that f of xy equal 5x minus 4y squared. Okay, here it is. There's your f of xy. Is differentiable as shown in this figure. Now it's figure 5 in your book, figure 4 on the slides here. Show that that is differentiable. So that's the first step. Okay, so let's do that. F of xy is equal to 5x plus 4y squared. Show it's differentiable. What's the condition? I started to write the partial, but they usually write the other way, so I'll do it the other way. What's the condition for that to be true? F sub x must exist. And what is that? Partial of f with respect to x.
That'd be
5. And partial of f with respect to y would be, I'm sorry, 8y. Both of those exist everywhere. Okay, 5 is 5 and 8y is 8y. No restrictions on either of those everywhere. Okay, so that's all we have to do. They exist and are continuous everywhere. Okay, so we've shown they are it's differentiable. Okay, find the equation of the tangent plane at AB equal to 1. So we want the equation of the tangent plane at AB equal to 1. Okay, so what do we need to do? Okay, we first need to plug in f of 2, 1, and that will be what? 10 plus 4 is 14. Got it. Okay, what else do we need? F sub x at 2, 1. What's that? Pretty easy. 5 is 5 everywhere. And what's f sub y at 2, 1? 8. Okay. Now what do we do with those 3 pieces of information? Said find the equation of the tangent plane. I like writing that z is equal to, which is 14 plus 5 times x minus 2 plus 8 times y minus 1. Okay, now that's probably not as pretty a form as we need to do it, so let's distribute, clear those parentheses. Z is equal to 14 plus 5x minus 10 plus 8y minus 8. Okay, what would that give us? Z is equal to 5x plus 8y minus 4. I don't know if that's the form they want it. They put the minus 4 in front. I don't know why, but that's perfectly fine. You see how to do that? Now, what's that? Okay. At that point, 2, 1, 14. Yeah, at the point. This is the tangent plane at the point P equal 2, 1, 14. Yeah. At that particular point, that is the equation of the tangent plane. Tangent plane through that point is that. Okay. Now, the assumptions matter. Remember, local linearity plays a key role. And although most reasonable functions are locally linear, the mere existence of the partial derivatives does not guarantee local linearity. This is in contrast to the one variable case where f of xy is automatically totally linear at x equal a if f prime exists. Just the fact you have the partials doesn't mean you got it locally linear. This one, yeah, no sweat, no problem at all there. Okay, because this is awfully close to the planar at that point anyway. In fact, the further up you get, the more close to planar it is. But it's not exactly. Okay, but if you had a function that has a discontinuity or a cusp or singularity or something else there at that point, or even real close to that point, everything may go haywire. So you have to have it true that it's a locally linear function. Okay. The next figure shows one that it's not locally linear. The closer you get to this, you still get lots of weird things going on. That's a paraphrase. Can I get it all in? Awfully close. Let's try it. Okay. Now, could have done better up top and bottom a little bit, but this one is side to side. Here's a function. G of xy equal to 2xy x plus y over x squared plus y squared. All right. Now, what is not intuitively obvious when you look at this, the point 0, 0 is not defined, okay? Not on the function, on the graph at all, because at 0, 0, you're dividing by 0. Of course, it's an indeterminate form, so maybe you're okay with that. But anyway, it's not defined at 0, 0. Now that may make you think things could be going wacko near 0, 0. Okay? Well, here's what we got. The horizontal trace at z equals 0 consists of the x and y axes. Here is that graph, whatever that is, and here the y-axis, there's the x-axis. That's all that's on that trace. Now, the way they've drawn this doesn't quite look like that's the case. And here's why I say that. No, I guess so. Yeah, I guess it's correct. Here the function is decreasing, going down here, coming back up, and so there's nothing except because everything in this quadrant here appears to be the first quadrant. Z is negative. Okay. But the whole graph comes down like this and goes up like that. Now, this is where it looks like it's real shaky in my mind, at least the drawing. For this to be true, that is the horizontal trace, this must be the maximum right here. And it doesn't look like it is. It looks like it keeps going up here and then turns and goes down again. If that were the case, there's some place in here where z is equal to 0 again. If this is positive here and negative down here, so to me there's a little something weird about the way this is showing. This has to be the maximum. And it looks like the maximum is somewhere out there. It can't be. It has to be doing this and going down in that quadrant, or octant, or wherever it is there. Okay? Then it comes up again and passes through the y-axis at z is equal to 0. So it's positive all here and here, and finally is, and this looks like, see, these two look like they are certainly right, but this looks like it continues to go down here and then come back up. And maybe it just doesn't get, it goes down here and coming back up, this must be the maximum again, and it just doesn't look like it. It looks like it's the line here where it's the max, which I guess it's just a distortion of the three-dimensional graph in 2 dimensions, you know. So anyway, they say that's the horizontal graph. But the graph also contains non-horizontal lines through the origin. Okay? So here as x is approaching 0 or y is approaching 0, everything seems to be hunky-dory. It seems like it's fine. But if you approach 0 from this way, that's a very steep line there. So it's definitely not approaching 0 in any dimension there. It's very low, small here, very large there. Very large slope in that dimension. In fact, both of these two dimensions, these and those. Whereas, this is harder to see if you are going downhill. Let's see. How can you describe that? Now there's something else squirrely here. If this is coming down here, but also going down here, if it comes up, it can't reach the plane again. I guess that's what's going on. Maybe. On these here, they've got so many lines here. This is your x-axis and the y-axis, these two here. These two are sloping up that way big time. I can't tell exactly where these are going here. This seems to be from negative z to positive z. The point is, as you go in different directions here, these are staying 0 and 0, whichever that is. This is a very large positive slope, a very large positive slope, going that way, and then things. So you have different values. The graph does not appear to any flatter as you zoom toward the origin. As you get closer here, it's still wacko here. You don't get any flatness because you have extreme valley here, let's see, valley here, but crest here. I can't tell what it's doing in those two, but it's going all sorts of different ways, and it doesn't get any better the tighter you get. It always has those same discontinuities. So obviously this one isn't locally linear, so don't even try to come up with a tangent plane on this one. If it's not locally linear, you just can't find the tangent plane because it doesn't exist. Okay. Now, example 2, I'm sorry. I believe this is the figure for it. Now here we're doing something a little bit differently or whatever. Where is this function, h of x, y, equal square root of x squared plus y squared? Where is it differentiable? Okay, that was the question. Where is this function differentiable? Well, that may not be a familiar looking form to you. Okay, but what would you do if you called this z, and then you had z squared is equal to x squared plus y squared? Now that's looking a little bit more like something we've seen before. And just looking at this, you see it's a cone, or at least half of a cone. You see, if you said z squared is equal to x squared plus y squared, then z could be negative, and you'd have the bottom half of the cone, too. But this, with it being defined to be only the principal square root, you just have the top half of the cone. Well, anywhere on the surface of that cone, you get close enough to local linearity. There's no way in the world you're going to get close to that here because it's going in a different direction everywhere around there. So yeah, it's differentiable. In other words, you should be able to see this. Let's do, I've got to shrink back. I don't need that. Okay. Let's do h sub x. First, I think I'd rewrite this as x squared plus y squared to the 1/2 power. So what would be your h sub x?
X to the -3/2.
Just x? Wouldn't it be?
Bring the 1/2 out, but then take the derivative of what's inside, right?
Okay, say that one more time.
So it'd be 1/2,
1/2.
but that's going to get multiplied by 2 at the end.
Right,
So
right,
it's just going to be 1.
right.
Yeah, I forgot about that.
And then you got a 2x. Right. Okay. So it's going to be x over the square root of x squared plus y squared. Right? By that? What would be your h sub y? Yeah, except it's going to be, the top's going to be a y. Right? Now, where do those exist? Everywhere but the origin, okay? Everywhere but the origin. At the origin, that doesn't exist, that doesn't exist. So, if the first derivatives don't exist in a place, they're not differentiable there, not continuous there, well, maybe continuous, but not differentiable there. And they must be, that's the requirement. Everywhere else, perfectly fine. Yeah, okay? X could be 0 as long as y is not, and y could be 0 as long as x is not, okay? And then any other values are perfectly fine, and you can do your tangent plane anywhere else. Okay. And in fact, the function, well, yeah, the function has got a value. So let's move to example 3. I think this is example 3. Okay. Find the tangent plane to the graph of f of xy is equal to x y cubed plus x squared at the point 2 minus 2. Okay? Thank you for drawing it for me. I sure didn't want to do that, okay? So you've done it for me, okay? So we need to find an equation of the tangent plane. So what are we going to need to do to get that? Okay, let me get that. Say again? Okay, partial of f with respect to x would be, got it? Okay. Partial with respect to y. Got it? Done. And you want those evaluated where? Okay. So f sub x at 2 negative 2 would be negative 8, wouldn't it be? Got it? And f sub y at 2 negative 2 would be yeah. Did you say negative? No, it's positive because the minus is being squared. 24, right? Correct? Okay. Right. F at 2 minus 2 would be negative what? I couldn't hear. 16? Yeah. Okay. So what is your tangent plane then? Z is equal to negative 12 minus 4 times x minus 2 plus 24 times y plus 2, right? Little bit of cleanup you can do here. Minus 12 minus 4x plus 8 plus 24y plus 48. That'd be z is equal to 48 and 8 is 56 minus 12 would be 42 minus 4x plus 24y. 44. Okay, sorry. Okay. 44. That's 40. 56 minus 12. Yeah, 44. Okay. That's the equation of the tangent plane. Now, second, at that point, 2 minus 2 minus 12. And let's see if the book got that. Hopefully they did. Yeah, 44 minus 4x plus 24y. Now, if you remember back to doing the simple things which we thought were so hard back in Cal 1, what's the equation of the tangent line at a point? Well, what did we do? We had to know the value at the point. The derivative gave us the slope at the point, and then using the point slope formula, we got it. Well, this is kind of like a point slope formula. There, the point, you just got two slopes, so you got this is the z value, and this is x minus the z value, y minus or plus the z value. So yeah, this gives you the slope in this direction, and the slope in that direction, and this is your composite of the z value from here to here and there. Okay, the change of this is the value you had to start with, and then you went up 8 there. It was a minus 12. This is the value you had to start with. You went up 8 and up 48. Up 8 when you went this way, 48 when you went that way, and these were the slopes. I mean, you started it. So yeah, it's a lot like it, except it's two-dimensional. So you got a lot more moving parts. Okay. And they say this figure is helpful. Okay. I'll take the word for that. The one in your text looks a little different from this one in that this one, it makes it look like the plane. I don't know what this coloration is trying to indicate. Looks like to me the plane cuts through under here, but over in these places. And I'm not sure that's what it looks like in your book. I think this may be a better picture in the book. Okay. Now, that done, linear approximation and differentials. Okay. By definition, f of xy is differentiable at AB. If it is, then it's locally linear, and the linear approximation is, this is the cheap way of saying it, f of xy is approximately your linearization. In other words, the equation of your tangent plane at xy for xy near AB. It's close. No cigars, but approximately the same. Okay? Now, what is, and of course it's going to shrink when I do this, what is this? This was our z, which is, still be approximate, f of AB, or we can call it xy, plus f sub x at xy I think we need ABs in here, don't we? Yeah, we got to have ABs in there. We can't have X minus X and Y minus Y. Okay. AB times X minus A plus F sub Y at AB times Y minus B. Okay? That's what this thing is. Okay? So that's what your F of XY is. Okay. Now, here's where the magic comes into play. Okay? All right. This is your x-axis, this is your y, this is your z. Okay? Now, here's your point AB somewhere out here. Okay? So this is your x value here, x equal A, y is equal to B, you know, that kind of stuff. Now, what if you were going a little beyond or one side or another of that value A? Then this would be your delta x, or this one or the other. Depends on if you're, which side of it you're on. Okay? Now, this would be your value x, or that, one or the other. Doesn't matter which. So you can tell from here that x plus delta x don't think I've got the sign right. Let's do it this way. Delta x is equal to x minus a. Okay? In other words, this is your delta x. And this is your delta y. Okay? How far they are apart from each other. So if that's the case, then your x is equal to a plus delta x. Okay? In other words, you're so far past that if delta x is positive, so far short of that if delta x is negative. Okay? And similarly, if y is equal to b plus delta y. Okay? Now, thinking of delta x, delta y as small changes x and y. So, let's go back to our formula here, and our f of xy here would then be f of, your x is a plus delta x, comma, b plus delta y. Okay. And this is approximately equal to f of ab plus f sub x at AB. And what do we just call that? Delta x plus f sub y at AB delta y. Okay, because that's how we define what our things were. Well, now this form is this, or at least close to it. Okay. Now, I'm going to highlight this, but then I'm going to modify it. Okay. What we were calling delta x, we're now calling h. What we were calling delta y is now k. Okay. So this is f of ab plus f sub x at ab times x minus a. Oops, yeah. Yeah, your h, if this was x, then h is x minus a. Yeah, and that's your k. All right.
And the new book left it in delta x, I guess.
What's that?
The new book, I guess, they left it in delta x.
Right. And that was my next point is that's how they did it in the old edition. And of course, I'm going to have to reduce this. So this is F of A plus delta X. Whoops. Yeah. B plus delta Y is approximately equal to F of AB plus F sub X at AB delta X plus F sub Y at AB delta Y. Okay? Now, what seems to be going on here, we went from a derivative type form to, now that's still a derivative type form here, but now we've got deltas in here, delta X, delta Y, and this is sort of your delta Z, kinda, a little bit, okay? And that, in fact, is their next statement, that this thing right here then would be what we were calling F at X plus delta X, B plus delta Y. That is, let's see, where am I? Okay. Where is it? There it is. Okay. That's your change of F. Okay. Now, difference in F is equal to derivative form. This is partial of F with respect to X times D. dx plus partial of F with respect to Y dy. That's your dF. And sure enough, it looks like the dx is canceled and the dy is canceled, and now df. Yeah, change of F with X. That's your total change of F. Kinda. A little bit. That is as close as we're going to get to a differential form here, I think. Okay. So, let's see. They don't show this, do they? Yes, they do. Surprise, surprise. Okay. Change that deltas to D's everywhere, and here's what you got. dF is equal to partial of F with respect to X, Y, dx plus partial F of X, Y, dy. Okay? Yeah. Now, what they slipped in on you, and I don't know, maybe you noticed it, but I almost didn't. Okay? It's this thing minus this thing. That's your change of F. Because this is with a little bit of change in both X and Y. And this is with no change of X and Y. So F minus F of this minus that, that's your delta F. Okay? This isn't your delta F. That difference between this and that, that's your delta F. That's where they sort of snuck it by you, or almost snuck it by me too. I was thinking that can't quite be true, and here's why, because both of the last two forms don't have the F term in there, because the change of F is the difference between the F with the deltas and F without the deltas. That's the change of F is equal to partial F dx plus partial Y dy. And written in more of a Leibniz type notation, partial F with respect to X dx, partial plus partial F with respect to Y dy. And a little bit of you might say, why is this a partial and that's a D? Why is this a D? Well, this is change of F, and this is change of X, change of Y, not holding anything else constant, just the change of that. So indeed, this is a D, and these are D's. But this is partial because you're changing only a portion of it, not the total of it. So get used to it. It's just done that way. Okay. Now, they extend things up to 3 dimensions too. Figures lose their meaning because you have to draw something in the 4th dimension, and I can't do it. They don't even try, okay? So let's see. Okay. I'm sorry, I sort of jumped a little ahead there. I forgot they had this graph here. All right. See if we can get our bearings on this. The quantity df this is no better than it was in the last book either, it may be identical. Make sure. Yeah, these are identical here. Oh boy. This is not an easy function to tell drawing to tell anything about. Okay? Obviously, the x-axis is coming this way, and the y-axis going that way. Okay? Z-axis is just hanging there without any relation to these two at all. I guess if you brought this on down somewhere and drew an x and y, that would kind of make a little bit of a sense. But I guarantee it. Okay? Now, wherever the x's and y are down here, these are your change of x's and change of y's. So we had a point here, and we're changing y's to there and x to there. Okay. This appears to be the point of contact. This is the place that defines your AB is right there. And this is F of AB. So that's the point where the tangent line touches the curve. Now, if you had a change in the y direction, you would be coming this way. And the change in the x direction would take you back that way. Okay? Now, this is the actual function value at xy. This is the linearization value at xy. Z is equal to L of xy. That's your plane. Okay? Now, if you move from the point AB to xy, then your function is actually changed from this value to that value. Okay, and measured on the z-axis, that is the amount of the actual change of the function, the delta F. The df is just the change of it on the tangent plane. Okay. And I don't know. That's all I can pick out of here that makes sense to me. And I really don't see a lot of connection with what we just did. But let's try it on example 4. And example 4 is not got a figure. So it says use the linear approximation to estimate this value. 3.99 cubed times 1.01 to the fourth power times 1.98 to the minus 1 power. Okay. And by the way, they've gone up to 3 dimensions. I probably should have done that first. So let me clear this. In the old days, I could grab it, lasso it, and haul it down. But let's do this. Okay. F of A plus delta X, B plus delta Y, C plus delta Z. Okay? Now, that's what we're trying to approximate. Okay? That's going to be approximately equal F of ABC plus F sub X at A, B, C times X minus, well, let's just do a delta X. That's what they do. I think we can live with that. This is differential form. Plus F sub Y at A, B, C, delta Y, plus F sub Z at A, B, C, delta Z. Okay. All right, that's just the extension of what we did in 2 dimensions here. Yeah, okay. They just wrote on 2 lines and I wrote on 3. Okay. Now with that in mind, here's what we're trying to approximate. 3.99 cubed times 1.01 fourth times 1.98 to the minus 1. All right. What function would you say we're approximating? X cubed, y to the fourth, z to the minus 1. Okay? Now, obviously, our x would be 3.99, our y would be 1.01, and our z would be 1.98. So what would be my A, B, and C, and what would be my delta X, delta Y, and delta Z? A is close to X. What would that be? It's close to 3.99. 4 with a delta X of 0.01. B would be 1 with a delta Y of 0.01 again. And C would be 2 with a delta Z of a little louder, negative 0.02, right? I don't guess I need the parentheses there. I thought it might make it clearer, but maybe it won't. Okay. Okay. Got that? Now. Okay. So, because the delta Z is less than 2. This is going down by 2. That's going up by 1. Oh, that should be a down.
Yeah,
That should be a down. Yeah. Oh, I'm sorry. Yeah. Negative. Yeah. Okay. Now, what else have we got to calculate? Yes, the partials. F sub X is equal to 3x squared y fourth z to the minus 1. F sub y is and f sub z is a cubed y to the fourth z to the minus 2. Got it. Okay. Now, our approximation, I don't know what to call it, but let's call it f of x, y, z. Okay. This is what this is. This thing right here. Okay. It's approximately equal to what then? Well, we start with this. F of ABC. What would that be?
32.
Say again?
32.
32. Wow. Okay. Yeah. 4 to the third power would be, what, 64 times 1. I can do that one. Divided by 4 is, no, divided by 2 is 32. Very good. Okay. What's our F? And this really should be, I'm sorry, I wrote that in the wrong place. This is F of ABC. Okay. Well, that's what I was writing there. Okay. Plus, okay, what is F sub X at ABC? Here it is, and that would be 3 times 16 times 1, I think I can do, divided by 2. Is that 24? And then what's our delta x? Negative 0.01, right? Right here. Okay. Plus F sub y at ABC. That would be 4 times 64 times 1 divided by 2. Is that 128? Okay. Plus 128 times 0.01. Right? Okay. Our F sub z, I'm going to put it here, F sub z at ABC. That's it. 412. That would be a minus 64 times 1 over 4. So that would be minus 16, right? Minus 16 times a negative 0.02. Right? So, what's this one? Minus 0.24. This is a plus 1.28. And plus 0.32. Okay. That's 1.6 minus 0.2, 0.24. That's 1.36, right? 33.36. Is that what you got? Okay. Okay, 33.36. Okay, with your good old handy dandy calculators, plug it in and see what we get. 3.99 cubed. I'm not going to do this one in my head. Times 1.01 to the fourth power times 1.98 or over 1.98. So 3.99 cubed times 1.01 to the fourth power divided by 1.98. $33.38. So we're awfully close. Awfully close. Now, doing it this way, here with real numbers in it, basically what that's saying is your F at that value is real close to what the F is here, plus that how much it changes per unit change in the x direction, that's the partial of F with respect to x, times your change with x, which is a negative, so that actually pulls it down some, plus the partial of this with respect to y in the y direction, times the amount it changes, plus, and this happens to be a minus here, the amount of change in the z direction times the change, the amount of change of f in the z direction times the amount of change of z. And that's what that gives you. Sure enough, it comes out really, really close. Okay. Did they get that too? Yep, they got 33.38 minus 33.36. Oh yeah, then use a calculator to find the percentage error. So what that is the difference between the two, 0.02 divided by the actual, which is 33.38, and multiply that by 100, make it percent, 0.075%. Pretty good. Okay, 0.00075. That's close. All right, let's clear those out of the way. What's that? Yeah, and let's see. We end at 140. Is that right? 155. Good. Okay. Whew. Glad y'all are keeping up. Okay. Getting on my class. No. Okay. Let's see if we can get example 5 done. Body mass index. I don't like this. A person's body mass index is I, that's the body mass index, is equal to W over H squared. Okay? Where W is the body weight. Did you see that? The body weight in kilograms. Boo hiss. What does kilogram measure? Mass. This is the mass in kilograms. Okay? And H is the body height. They got this right in meters. Right? Yeah. So that's the mass. I probably should put those more equivalent. Okay. Now, fortunately, I don't know my body mass or height in kilograms and grams, but let's say in meters, okay? Estimate the change of a child's BMI if WH changes from 40, 1.45, that's 40 kilograms, 1.45 meters, to 41.5, 1.47 meters. Yeah, I was going to put units, but I probably shouldn't. Okay. Now, estimate the change of the child's BMI. All right. Say again? Yes, exactly. So, I sub W would be what? Perfect. And I sub H would be, let's rewrite this as W times H to the minus 2. Right? Taking derivatives, you subtract 1, right? Got it right? Okay. Now, in this case, I would use the original as my basis, okay? And then, so my A would be 40, my B would be 1.45, my delta W would be, say again? $1.5. And the delta H would be 0.02. Okay. Okay. Now, and they're asking for change, right? Estimate the change in the BMI. Delta I would then be approximately equal to I at AB, we don't have a C in this one, plus I sub W at times delta W. I'm really abbreviating like crazy here. Plus I sub H times delta H. Okay, so in other words, your starting value plus how much this changes for change of this times the change of this plus how much that changes for change of that times the change of that. That's what we're doing. That's what we're estimating. So what is our I at AB? Oh, wait. They're asking for delta I. I'm sorry. The delta I would just be, take this out because that is the difference. The I, your projected I would be what we had there. The delta I is the difference between that projection and what we got. So the delta I is just going to be this amount. You see that? This is how much it's changing. So what is your I sub W? This is 1 over 1.45 squared times 1.5 plus minus, okay, two times 40 divided by 1.45 cubed times 0.02. That's your change of I. That is your projected I minus that original. So you don't have to calculate the original. I thought we did, but we don't. Okay? So someone's got a calculator. This is going to come out just a little bit more than 1. No. No.
1.45 squared, that's 0.47. Around that, that's going to be 0.48. And then
Well, what? Did you multiply that by 1.5?
39.36. Yeah. This is 1 over 1.45 squared times 1.
This. Okay. Oh, okay, this. Okay. Yeah, I don't have a calculator, so I can't do it. So, see, you
I got 1.18.
What's this?
Oh, the first part?
Wait, no. Your total is what?
1.9.
1.9.
0.19.
0.19. Now, that sounds pretty reasonable. Because I don't know what the book got.
The first part's 0.713.
Okay.
40 minus
We should probably do it for parts.
Okay, what'd you say, 0.19 something? They said
the
0.2.
first part,
Yeah.
before you minus the other thing,
Right.
it's 0.713.
0.713. Wow. Yeah, okay, 0.713, right? And this part over here is not that big, but close to it.
1.713, I got that. Yeah.
But yeah, you did it all at once and it came out exactly what they did, 0.2 approximately. So the body mass index didn't change much. The kid went up in mass a fair amount, but also increased height a little bit. But because of the ratio, 0.18, that rounds to
0.19,
that rounds to 0.2. The book rounded to 0.2.
Okay.
Yeah. So y'all got it. Okay. It increased by about 0.2. Okay. If he had grown a little bit taller, he would have a negative body. His body mass index would have shrunk a little bit. But he put on a fair amount of mass for that little bit of height change, so it did go up a little bit.
It's funny though, they don't, if you have over a certain amount of body mass index, that insurance companies and such don't like that. But
Right.
sometimes it can be muscle and not fat.
Exactly.
It can be more healthy, but still have a high BMI.
Right. Homework exercises here. Do 1, any of the odds 3 through 9, any of the odds 11 through 21, any of the odds 23 to 27, and then any of the odds 29 through 37. And we'll begin on 14.5 next time. Good deal, folks. If you'll hit the